Hello everyone. In this video we are going to try and understand what a confusion matrix is, how to construct a confusion matrix, as well as subsequently derive various evaluation metrics using this confusion matrix. So to begin with, let us look at some images of cats and dogs. So on the left side we have 3 images of cats, and on the right side we have 3 images of dogs. Now that we have established this, let us see what our model says regarding the labels of these images. So we can see that our model has predicted the first 2 images as cat, whereas the third image it has mistakenly labeled it as a dog. Likewise, when it comes to the images of dogs, the first 2 are correctly predicted as a dog, whereas the third image is that of a cat, which is an incorrect prediction. Now we have this matrix or table of sorts on the left side, where we have written predicted label on the bottom and true label here. So what this means is that if the true label is cat and the predicted label is also a cat, we want it to come in this cell. And if the true label is cat but it is mistakenly predicted as a dog, then we want it to come on this cell. So let us try to fill up this table using the images we have here on the right side. So let us start with this image. Since both the true label and the predicted label was the same, and that is that of a cat, we have put it in this particular cell. And as we continue with the other images, we have the dog, and here it was predicted as a cat but it's actually a dog, so it's in this cell. And likewise, this is actually a cat but it is predicted as a dog, so it is in this cell. Adding all the images, we can see that the matrix is filled as so. And just to reiterate again, we have this matrix of sort with 4 cells, this cell being a true label cat and a predicted label also a cat, this one being a true label dog and predicted label also a dog. This is where a true label is cat and it has falsely predicted it as a dog, and here its true label is a dog and it is falsely predicted as a cat. Now we will go to a slightly different data set. Now so far what we had seen was a binary data set, that is there were only 2 classes. But now let us take the case of the MNIST data set. So MNIST dataset is a collection of 70,000 images of digits. So the digits are from 0 to 9, that is you'll have 10 of them. And the way it is stored is of a row of 784 values or features, and we can reshape it and we can get back a 28 by 28 image as shown. So this is a sample image of the digit 0, and if we look at some of the other data points, it is as shown here. So as you can see, there are multiple instances of 1, multiple instances of 0, as so on for all the digits. Now what we want to do is we want to slightly modify this multi-class prediction problem into a binary prediction problem, where we only care if our model can predict 3 correctly. If it is any other digit than 3, we want it to predict it in the other class. So this is sort of an example matrix we will get in such an situation, where we can call the positive class to be one where the model correctly predicts it as a 3, and any other digit it has to go to the negative class. So if the image was actually of a 3 and it was also predicted as a 3, it is in this cell. And if it is not a 3 and originally, and it is also predicted as such, it will come to this cell. So we are calling this one as true positives, this one as true negatives, and here we have a cell where the image was falsely predicted as positive. That is, it is actually negative, that is not a 3, but our model has falsely predicted it as 3. Likewise, here in this cell we have false negatives, where its actual label is that of 3, but it is falsely predicted in the negative class. So now let us come to the confusion matrix. What we have seen so far, we have directly seen the data points itself, but the confusion matrix tends to have the number of instances rather than the instances themselves. So what this particular matrix means is that here it's a multi-class setup where there are 3 classes, and the number of points where the true label was 1 and the predicted label was also 1 is 16. And 2 of those instances where the true label was 1 but it was falsely predicted as 2, and another 2 instances where the true label was 1 but it was falsely predicted as 3. So totally we have 50 instances in this, and you can also verify it by summing up the rows. So there were, in the original data set, there were 20 points that were of label 1, 20 points that were of label 2, and 10 points that were of label 3. So just like how we have understood for 1, we can also understand the other ones, that is the middle one here. the true label is 2 and the predicted label is also 2. So we have 15 such instances, and 5 instances for 2 were misclassified either as 1 or as 3. Now that we have this, let us actually construct a confusion matrix given the true and predicted labels. So here we have the true and predicted labels in a table, and we want to fill up this confusion matrix. So first let us take this particular cell where we only want to consider the instances where the true label is 0 and so is the predicted label. As you can see, there are 4 values highlighted, which is why we can write the number 4 in that particular cell. Moving along in the same way, the number of instances where the true and predicted label match for the class 1, there are 3, so we have written here the value 3. Likewise, we can fill up the other 2 cells also, and this is how the confusion matrix is considered in a constructed in a binary classification problem. Now the same thing can be extended to a multi-class classification problem, where the only change is that instead of 2 classes as we had previously here, we now have 3 classes. Likewise, the matrix also, which was a 2 by 2 matrix, is now going to be a 3 by 3 matrix. So we have this 3 by 3 matrix here, and the same idea will be followed, that if the true label is 1 and the predicted label is 1, we put it in this cell, and in this given data there are only 2 instances, which is why it was 2, and likewise all the other cells also are entered in the similar fashion. Now how do we interpret this confusion matrix? Now what we can consider is, we can take the statement that says all images of dogs have been correctly identified from the dataset. So if you go back to this initial images that we had seen, we had images of cats and dogs, and if you were given a task saying I want to be able to correctly identify the images of dogs from this dataset, and the model gives out, like from the model, if you can make a statement saying all images of dogs have been correctly identified from the dataset, it does not necessarily mean it is a good one. So now if you look at the confusion matrix, what we end up seeing is, if class 1 had been that of a dog, all instances, that is, if there were 10 points, all of them would have been classified as a dog. It means that no matter if you give the images of cats or dogs, your model would have always predicted it as a dog, making it a bad model. So this is a way in which you can make use of the confusion matrix. Here, as you can see, the model performs poorly for class 0, but performs quite well for class 1. Now if we consider another case where it says the performance of the model is in any given class is similar, but if your confusion matrix is as seen, it shows that your model has not really learned much, because it is not there are equal number of values in the false positives and false negatives as there are in true positives and true negatives. It means that your model is not able to identify even a single class correctly, and it might as well have been giving a label at random. So that is it for this video, and subsequently we are going to see how we can make use of this confusion matrix to get down some evaluation metrics such as accuracy, precision, and recall. Thank you.